In part 1, I built a device based on a trebuchet to launch an egg as far as possible. The idea is to enter it into the Fieldhouse Challenge Eggapult competition. So it has to be below a certain weight and size, and can only use energy stored in a raised weight. Try as I might, I couldn't fire the egg further than 6 meters. Though theoretically much more than this is possible. The main problem I faced was transferring the potential energy stored in the weight to the egg without the entire trebuchet being thrown in the opposite direction. I decided a completely different approach was necessary. There is a clause in the rules that states the energy can change form after the device is fired. What this means is the counterweight doesn't have to be directly acting on the projectile. I can put a spring in between. But how can this possibly be better? Each time energy changes form, some is always lost through heat, friction, etc. Adding a spring can never deliver more energy in total. Also, the spring itself has some significant mass, which due to the weight limit means less mass for the counterweight, therefore less energy to start with. So the direct acting weight seems like it should be the winner. However, there are two clear advantages to putting a spring in between. Firstly, the weight can only fall as fast as gravity pulls it. But if the same energy is stored in a spring, the spring can snap back almost immediately. So the spring should be able to transfer its energy to the projectile more efficiently. Or rather, the force it can exert is much less dependent on how fast it's moving. Secondly, and the main reason I decided on this approach, the weight can do double duty. After the weight has transferred its energy to the spring, it can be locked to the frame, acting as an anchor and providing a more stable platform from which to launch the egg. The other end of the spring can then be unlocked to fire the trebuchet. Hopefully, that will stop this from happening. All this must be controlled mechanically without any sensors or electronics, since batteries are not allowed. As previously, I'm starting with a simple proof of concept test. Just a spring attached to an arm. No weights or triggers. When I pull back the arm, it stretches the spring and stores around 5 joules of energy. The equivalent of lifting 2 kilograms, about 250 millimeters. Hopefully this will be better than the counterweight trebuchet. The number to beat is 6 meters. Four meters. That might seem a little disappointing, because it is. But I still think this spring method can work. I just need to fine-tune it a bit to get better results. I have these springs which came from a trampoline. Even though they're the same, they're all slightly different. The arm latches in place when the counterweight is at the top. It's released when the weight reaches the bottom. As the weight falls, the pivot point at the bottom of the spring goes sufficiently over center that the spring can't pull the weight back up again. The weight comes to rest on the frame at the bottom, holding the frame down when the spring is released. In the center is an equilibrium point where the force on the spring balances the gravitational force on the weight. Only half the available potential energy has been transferred to the spring at this point, and the weight relies on its momentum to get past it. I haven't made a proper trigger yet, so for now I'm just pulling this block out from under the weight near the end of its travel. Nope. 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 Still nope. What's going on here? The weight is preventing the frame from lifting up as it should. But now the arm is still moving quite fast after releasing the projectile, and as the spring catches it when it passes over the top, this causes the frame to slide out from under the weight and the whole thing falls over. The best range I got from any of these tests was 6 meters, better than 4 and no worse than my previous Trebuchet design, but I need to do better. Watching the footage in slow motion, I noticed something interesting. The arm accelerates to start, reaches a constant speed, slows down, stops, even goes backwards slightly, and then carries on again. Why does that happen? In Trebuchet speak, this is what I believe is called a stall point. It happens because the sling with the projectile moves outwards further away from the pivot point of the arm, so increasing its reactive torque. Just like using a cheetah bar on a spanner. It eventually becomes so great that it can even cause the arm to move backwards against the spring tension. Notice where the stall point occurs, between 90 and 45 degrees before top dead center. I had previously assumed the best point to release the projectile would be when the arm is all the way up vertically and the sling is at an angle of 45 degrees. 45 degrees is the optimum launch angle for the furthest range. And if the arm is right at the top, then that's the highest point to start from. So I designed the trebuchet around this assumption. I realise now this was wrong. If I can time things so that the stall point occurs at 45 degrees and release the projectile here, I should be able to transfer much more of the energy to the egg, and the arm should be moving much more slowly after release, so the whole thing shouldn't topple over. I originally designed the trebuchet so that the spring doesn't release all its tension until the arm reaches the top, so I had to change the spring and make a new counterweight arm so that the spring transfers all its stored energy by the time the arm reaches the stall point. A big improvement. And a new record. 7 meters. Time to make a proper trigger mechanism. I also experimented with adding small weights to the end of the arm to try and tune the stall point. Another way to do this would be to make the sling longer, but I don't have space to do this without the strings becoming slack, which caused problems. Too little weight, and the arm still gets pulled backwards. Adding more weight causes the arm to just pause briefly and also increases the angle of the stall point towards 45 degrees. These improvements have got me to 8 meters, but I think I can still do better. I noticed that the weight still lands with a lot of force, wasting energy that could go into the spring. So the spring needs to be stiffer. I modified the old spring by taking off some turns. I think I overdid it. That was a solid 9 meters, but it's too unreliable. Only 3 attempts will be allowed in the competition. So I made another spring, experimented with different weights, modified the frame, shortened the counterweight arm, and the best I could come up with was this. It looks quite smooth and stable during firing. But it still won't do much more than 9 meters. I think I've reached about the limit of this design, which is a shame, as I was really hoping to make double figures. If I were to start again from scratch for a third time, I'm confident I could add maybe another meter or so. But I think now, enough is enough. So here are the final specs. It measures just under 300 millimeters tall and long. The 3 scales I own couldn't agree exactly on the final weight, so I went with the most pessimistic one, and removed 15 grams from the counterweight, bringing the weight to just under the 3 kilogram limit. The counterweight takes up 2.2 kilograms of this, and when raised, stores 5.4 joules of energy. Now, I know you probably want to see me launch a real egg, so here goes. In the actual competition, entries will be placed on a platform 1 meter above the floor. The top of this table is exactly 1 meter above the lawn area, so let's see how it performs under tournament conditions. The extra height should add a similar amount to the range. The measurement criteria is the furthest part of the yoke that's at least 10 millimeters diameter, which would be here. That's 10.15 meters. So, do I think I stand a chance of winning with this design? Well, a chance maybe, but it's not a sure thing. 2.22 kilograms raised to 248 millimeters is 5.4 joules. For every action, there is an equal and opposite reaction, so if this energy is shared equally between the trebuchet and the egg, then the theoretical maximum range is 9.17 meters, almost exactly what I achieved on a flat surface. However, if you consider some more complex physics, like the conservation of momentum, this shows that it's possible to share the total energy unequally. This means somebody else is in with a definite chance of beating me. Who knows, maybe somebody has built something really basic out of elastic bands, which somehow is just more efficient than my design. Or maybe something extremely advanced from titanium, carbon fiber, and superconducting magnets that pushes the laws of physics. I'll just have to wait and see. But you should be able to find out already, since I'm not going to post these videos until after the competition. So check out the Fieldhouse YouTube channel, link in the description, and tell them I sent you.